Welcome, everybody. We're happy to have Hannah Banks today. So Hannah just told me she was an undergrad at Imperial and then moved to Cambridge for a PhD and stayed on there for a postdoc in particle theory. Although I guess around that time you started thinking about quantum sensors and in particular mechanical quantum sensors for things like probing the precision frontier of physics, including searching for ultralight dark matter. And then recently, I guess in October, Hannah's moved to NYU. So we were happy to have her just take the train this morning to come tell us about some of the things she's been thinking about using quantum systems to search for dark matter.
Awesome. Well, thank you so much. Thank you so much for having me here. I'm honestly, we say I've been like a kid in a sweet shop seeing all the stuff you're doing in the lab. So as Dave said, I'm not an experimentalist. Unfortunately, I am a particle theorist, but I'm hugely excited by what the developments are going on in the lab. And I'm excited to talk to you about that today. But I think it's 2026 now. And as a fundamental theorist, I feel that we really are at a crossroads. We have this abundance of evidence for new physics beyond the standard model. Yet, despite pretty relentless searching, which has encompassed all manner of kind of direct, indirect detection, collider experiments, we still don't know what 85% of matter in the universe is. And to me, that's really quite a humbling thought. I think to capture kind of the state of our ignorance, change slides, we have this plot, you've probably all seen this before, which tells me that if dark matter is a single fundamental particle, and that in itself is quite a strong assumption that dark matter is just made up of one new thing, it could be anything ranging from all the way 10 to the minus 22 electron volt ultralight bosons, all the way up to like post-Planck mass primordial black holes or like macroscopic objects. And this is really quite a bewildering array of masses. And you can imagine that the phenomenology that this gives rise to is similarly diverse and rich and worthy of exploring. Now, up until this point, the majority of searches have largely focused on this kind of like WIMP model. So you're probably all familiar with the WIMP. It's a GeV mass-ish particle that potentially scatters with the standard model. And therefore, your signature is going to be like an impulse. Okay, so that if you're looking for a WIMP, you're looking at like typical impulse-based detection. However, once you start going away from this, you can start getting a lot of very, very different phenomenology. And in turn, that's going to require you to detect it in a different way. So today I'll be focusing particularly on this ultralight regime, which is just dark matter, which is sub-electron volt. And it turns out that this type of dark matter actually behaves like a coherently oscillating wave. And again, I'm not an experimentalist, but I think even in my head, it's kind of clear that if I want to detect a wave, I'm going to have to detect it very differently to if I detect, for example, a WIMP. And this is really giving into some very interesting avenues for detection. Now, you might say, well, why did we focus on the WIMP to start with? Well, the WIMP, from a theoretical perspective, people like the WIMP. You may have heard of the WIMP miracle. It so turns out that if you try and produce these things in the early universe, they end up with the right abundance to meet dark matter. But partly the reason why people focus so heavily on searching for the WIMP was partly because the technology just happened to be in the right regime. I'm not saying it was like people were like, oh, we could just go and like do it. Obviously, there still had to be technological developments, but in terms of like compared to this kind of ultralight regime, the WIMP was seen as a much more accessible target. And I think that's partly what drove this kind of influx on the WIMP. But because our searches for WIMPs our searches for dark matter have concentrated on these kind of WIMP-like particles, that leaves a whole array of this landscape really very underexplored. And it's only really been in kind of very recent years where there's been kind of transformative advances in quantum sensing technologies that we've actually been able to reach the kind of precision required to probe these new light models where instead of your new particles being hidden behind an inaccessible energy barrier, they're hidden behind incredibly feeble couplings to the standard model. So that's what I'll be focusing on today. Now, why does it oscillate? So apologies if this is a bit technical, but basically if you add any new very, very light particle to your standard model, it's just a free scalar, and imagine that in the early universe, this particle sits in some potential. Imagine that at the beginning of time, it's not quite at the minimum. I mean, why would something be at the minimum? It's slightly displaced from its minimum. And if you just let this evolve due to cosmology, what you find is that at late times, this particle is oscillating about the minimum of its potential, okay? So you've got a wave-like thing. And it turns out you can treat this completely classically. So again, you're probably all aware if you've got like your phase space density is very, 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 very high, all the quantum effects are washed out. And because the mass of our dark matter is like sub-EV, if you want to saturate the abundance of dark matter that we know that we have in the galaxy, your number density has to be extremely high. And as a result, we basically have this classically behaving oscillating wave. And this is kind of the sort of generic class of what we mean when we say we're searching for ultralight dark matter. So as you can see already, this looks very different to kind of think about, thinking about particle scattering or things like that. Okay, so it turns out that when I say ultralight dark matter, that's just kind of an umbrella term. And that really just describes anything which is lighter than about an electron volt, so has this wave-like behavior. Now, in terms of actually detecting this in the lab, they all have the property that they're oscillatory, but you can get various different types of signature, and we can compactly characterize the signature that we're looking for by the spin of the particle. So if you have a scalar particle, so there are various different well-motivated examples from theory. People talk about moduli and dilitons, which come from string theory. There's the relaxion, which solves the electroweak hierarchy problem. Higgs portal dark matter, which is just a scalar which couples to the Higgs. All of these things actually cause fundamental constants to appear to vary in time, which is a very, very bold statement. And I'll explain a little bit more about why that is and the sort of signatures that can lead to in a second. The second type of dark matter is also spin zero, but this time it has pseudo-scalar couplings, so CP odd couplings, the standard model. And this is your typical axion in the out that you're all familiar with. And in terms of detecting this in a quantum experiment, well, of course, you can do like a haloscope experiment, so ADMX or haystack, and there you're looking for the conversion of axions into photons in a strong magnetic field. But actually, in a kind of more, in a not electromagnetic detection, the way of doing this non-electromagnetically, you'd look for spin-dependent effects, so time-dependent, spin-dependent effects. So pseudo-scalars coupled to spin, scalars coupled to mass, and that's kind of the difference that we have there. Now, ultralight dark matter doesn't need to be a scalar, it could be a vector. And in this case, again, there are different theories that people have. We have dark photons, which is just basically like a photon, but it only couples to the standard model via kinetic mixing with the normal photon. So you get mixing, like oscillations between the dark photon and the photon. And again, that can lead to kind of spin effects. It can also lead to effects in electromagnetic cavities. And the second type is when your new particle has a direct coupling to the standard model, which is the example that I'll focus on today. And in that case, we call it, for example, B minus L, which is baryon minus lepton number. All it means is that your vector is coupled in a way such that the baryon minus lepton number is conserved. And that leads to oscillatory forces, which again is something which we can detect using, for example, optomechanics. So I'll be giving you various different ways that we can search for these. To start with, I'll talk about detecting scalar dark matter with atomic clocks and interferometers. And then at the end, I'll talk about oscillatory forces with optomechanical systems. So I want to just start by introducing this spin zero scalar ultralight dark matter and how it causes fundamental constants to oscillate in time. So apologies if you're not particle physicists, you may be looking at this and going, go away, Hannah. But I'm going to go through this hopefully and it will make sense. So if you just have the standard model, so if you get rid of everything that I've got in pink and orange here, you just have a term that looks like ME E bar E. Okay, so that's just the electron mass. So when you have ultralight dark matter that's a scalar, the kind of rule in particle theory is if you add a new particle to your theory, you need to add on every coupling which is consistent with your symmetries. So all I've done here is I've added on a new scalar, and this scalar is now coupling to this term here with a coupling constant ME. Okay, so you can imagine you now have the mass of the electron plus an extra contribution, which depends on phi. Okay, and phi is oscillating. Okay, so this means that the mass of the electron is going to oscillate. And it's not just the mass of the electron that's going to oscillate. You can have it coupling to quarks, and then the quark masses will oscillate. So the proton mass, the neutron mass will oscillate. You can have it coupling to photons. This means that the fine structure constant alpha is going to oscillate in time. And you could also have it coupling to gluons, which means the strong coupling constant is going to oscillate in time. So as a result of adding this new, if this scalar exists and this scalar couples to the standard model, what you find is that all of the fundamental constants are going to appear to oscillate in space and time. And why is that significant? Well, everything in nature is built from fundamental constants. So every energy scale we have, every length scale we have, they're built from these fundamental constants. So if your fundamental constant is oscillating in time, every energy scale that we can probe, every length scale we can probe is also going to oscillate in time. Now, of course, this oscillatory is the extent to which it oscillates, sorry, I can't speak today, depends on these coupling constants, and we think these are incredibly feeble. So as a result, you need to be able to make very, very precise measurements if you want to be able to detect these things oscillating. So where are some examples of places where not only do we have high control over the precision that we're measuring things, but they're sensitive to energy and length scales? Well, one particular example is an atomic clock, okay? Does anyone work on, do you have any atomic clock people here? Just checking, okay. If you do know more about atomic clocks than me, feel free to tell me that I'm talking rubbish, but my understanding of atomic clock is you have a two-level system, so you just have a ground state and excited state, it's stable, and you have some energy difference, omega-1, between these two states. Now, it turns out that the energy difference between these two states, atomic theorists, they can go away and they can calculate and they can say, okay, well, the frequency or the energy of this transition has some formula depending on the fundamental constant. So the fundamental constant is the fine structure constant, the electron mass. So again, you're probably all familiar with the formula for the hydrogen atom. The hydrogen atom levels are set by the mass of the electron and the fine structure constant alpha, okay? And it turns out that every different clock transition, so every different system that you're probing, has a slightly different dependence on these parameters, right? We can characterize the extent to which the transition depends on these parameters by this enhancement factor. So this is literally just saying the derivative. So all this enhancement factor is telling me is, how does my transition energy depend on each fundamental constant? Okay. And how does this give us a way of being able to probe dark matter? Well, if you have two different energy levels and your energy difference is oscillating in time, if you then have two different clocks with different dependencies, what you'll find is that the energy difference, if you compare the frequency of this and you compare the frequency of that, you'll see that the frequency that you're comparing is also going to oscillate in time. And the amount that it oscillates in time depends on the difference between these two constants here and here, okay? So if you want to build a really good atomic clock experiment, what you need is two different clocks which have very different dependencies on fundamental constants, so very different K factors. Everyone with me so far? Okay, great. So again, the signature you're looking for with an atomic clock is an oscillating energy difference, okay? Now, up till now, the best kind of atomic clocks have been optical transitions, so where the photon that you're interrogating or the laser that you're using to interrogate your clock is an optical transition. And you're looking at, again, transitions in energy, in electron levels. And it turns out that these, much as we know about the hydrogen, these transitions depend on the fine structure constant and the mass of the electron. So going back to our dark matter theory, that means I can probe this coupling constant Me, which is the coupling of dark matter to electrons, and this one, which is the coupling of dark matter to photons. So those are the couplings that I'm able to probe with a typical optical clock. Now, I'm going the wrong way. What am I doing? Sorry. Get there eventually. Right, good. So that's an optical transition. Now, you can imagine that the energy level of your hydrogen atom, for example, is not really going to depend on the mass of the proton. And therefore, that means that anything coupling to gluons or quarks is not really, you can't really use an atomic clock with it. So you can't use an optical clock with it. But it turns out that microwave clocks do have some sensitivity to these things. And I should probably mention that the typical size of these enhancement factors is like order 1 for an optical clock. For a microwave or a hyperfine clock, you can get an order 1 K factor for G and M. So if you compare a microwave clock to an optical clock, then you can get a difference there. So the main point I'm trying to say is that you can probe couplings to electrons, you can probe couplings to photons just with optical clocks. If you then compare them to a microwave clock, you can actually begin to probe gluons and quarks. And that's kind of the state of atomic clock physics at the moment. However, the reason why I'm telling you about clocks is not really because of the atomic clock. It's because you may have heard of this, thorium-229. This is, in my opinion, one of the coolest things, which is I'm hearing about at the moment, which is the nuclear clock. So people recently discovered this isomer of thorium-229 has an excited isomer, so an excited state, which is actually stable. And what's really cool about this is that the energy difference between the ground and the excited state is only 8.3 electron volts. And you guys know better than me that 8.3 electron volts is optical, well, slightly in the UV, but it's, you know, it's something that you could drive with a laser. Now, typical nuclear transitions are on the order of mega electron volts. So the fact that we have a system with such a small energy difference is hugely exciting, because it means that we have the potential to be able to drive this thing with a laser and actually build a clock out of it. And this really is kind of one of the mysteries of the universe, I think, because, as I said, typical nuclear transition energies are mega electron volts. So why have we got this 8.3 electron volt? It's the only nucleus that we've found that has this desirable energy transition. And it's really due to a finely tuned cancellation between the strong coupling and the weak, so the strong contribution and the weak contribution to this energy. So it's like you've got like a really finely tuned cancellation. So it's a freak of nature, something which people as theorists, people normally get very unhappy when we have a finely tuned cancellation. But here it's great because it means we can build a nuclear clock. So why would you even care about building a nuclear clock? Well, one reason, purely experimental, is that if you're looking at a nuclear transition, your nucleus is surrounded by electrons. So the electrons are actually shielding your nucleus. And as a result, you're going to be far less sensitive to kind of stray B fields and things which would affect your transition energy. But from a fundamental physics reason, the reason why I'm excited about the nuclear clock is it turns out that the nuclear clock is extremely sensitive to the variation of fundamental constants. So before I was telling you about optical clocks, and I was saying, oh, their K factors are like order 1. Nuclear clock, order 10 to the 4, 10 to the 5. Now, I don't know about you, but when someone comes to me and they say, oh, I've just built this new experiment, I can get like an order of magnitude improvement in my bounds. And I'm like, yes, that's amazing. Here we're talking about 4 orders of magnitude, and that's literally just from changing the atom that you're using for your clock. Okay, so that's hugely exciting. And this is 4 orders of magnitude in the coupling to electrons. Now, if we look at the coupling to quarks and gluons, now for a typical atomic optical clock, so not hyperfine, but actually optical, this, as I said earlier, this is only sensitive to these couplings through the mass, like ME over MP, which is like 1 over 2,000 or whatever. So the mass of the reduced mass of the system, basically. So for an atomic clock, it's 10 to the minus 5. Here it's 10 to the 5. So that's a 10 orders of magnitude enhancement in coupling to quarks and gluons. So this really means if you could build a system, you'd really have incredible sensitivity to new physics coupling to the nuclear sector, so to quarks and gluons. And this is a hugely exciting prospect, and it's something that I'm very excited about, you can probably tell. Now, you might be thinking, well, okay, so is this like realistic? You know, what is the state of this? Well, they haven't. The caveat, of course, is that we haven't actually got operational nuclear clocks at the moment. But the state of progress is extremely rapid. When I started thinking about this, I was working at CERN at the time, and they have the Isolde facility there where they're actually like isolating the thorium. And at the time I was talking to people and I was like, wow, you know, when do you think you might, you know, be able to, you know, build these clocks? And they were like, well, at the moment we know the transition is about 8 electron volts. We don't know quite where it is. We can't like excite it because it's a very weak transition. So you need a lot of laser power to be able to excite it. So they knew it was there, but they hadn't been able to radiatively excite it. They're like, maybe in about 5-10 years, you know, hopefully we'll excite it. Within a few months, not only they had excited it, but Junyi had gone at Julian, he'd gone and put a frequency comb on it, and they then improved the sensitivity. And I think it's now in like 1 part in 10 to the 8 or 10 to the 10. Like it's the rate of progress, but they've now isolated this transition. Not only have they been able to excite it, but they're now doing spectroscopy on it, and it's really quite incredible what they're doing. So this for me is a really exciting prospect. And it turns out that, I mean, at the moment they haven't got an operational clock, it's not like stable, but they are doing spectroscopy on this line shape. And already there's a paper that was out maybe like a week ago. And just from analysing the line shape of the spectral line, they've already got new bounds on ultralight dark matter, which beats what they can do with atomic clocks. And this is before they've even been able to do like a frequency comparison experiment. So this to me is hugely exciting. And it really kind of, I think, warrants people giving thorium-229 more kind of thought and perhaps thinking about other ways which it could be used. So again, clocks is kind of the obvious thing, but there might be other ways in which the sensitivity of thorium-229 could be exploited to search for fundamental physics. Okay, cool. So I've talked about clocks looking for oscillating energy differences. It turns out there's a way that you can apply clocks, another way that you can apply clocks to look for ultralight dark matter, which is actually atom interferometry. So again, this is just an experiment which measures the phase shift between spatially separated quantum superpositions of wave packets. So you're probably all far more familiar with this than me, but back when I was an undergrad, I remember having to do like Mach-Zehnder interferometry with light, and we had beam splitters, and I was awful at it. I wish I wasn't, but I was. But this is exactly the same thing. It's a Mach-Zehnder interferometer, but instead of using light, you're actually dividing your wave packet into two parts, into a grounded and excited state. You're then letting it propagate, recombining it, and measuring the phase at the end. So how does this work? Well, again, just in case, I mean, you're probably, again, more familiar than me, but if you've got any two-level system and you couple a driving force to it, what happens is the probability of being in the ground and the excited state oscillates in time. So if you start in the ground state, you apply your laser pulse after some finite time, you expect 100% transition probability to be in the excited state. If you only apply your laser for like pi/2, you find that you get into the superposition. So this actually allows us to be able to build an interferometer. So your pi/2 pulse acts as a beam splitter. It drives your ground state into a superposition of ground and excited. And again, you can do a pi pulse. So in this case, you start in the ground, you apply your pulse for pi seconds, and you end up in the excited state. So now let's build the interferometer. So you start in the ground state. What you then do is you apply your pi/2 pulse, so that splits it into ground and excited, and you then let these things freely propagate. So in practice, what they do is they have like 100-meter, well, not necessarily 100-meter yet, but they have like a kind of, they literally have an atomic fountain, and they shoot these things up, they apply the pi/2 pulse, and they let it drop under gravity. So you have these two things. You all know from quantum mechanics, if you've got any energy levels, the rate of phase accumulation goes as e to the I et. Right? That's the rate that phase comes. So if you've got two different energy levels, ground and excited, they're going to accumulate phase at different rate. The excited state will accumulate phase faster. So what you find is that as you let these things propagate, you get a phase difference between these states. After some finite time t, what you then do is you reverse the momentum. So in fact, you go from ground to excited, excited to ground, but because you're emitting a photon, you're transferring momentum, essentially. And you let these things come back together, and then you interfere them by using a pi/2 pulse. And what you then do is you have two detectors, one which has the ground state and one which has the excited state, and you count the number of atoms in each detector at the end. So why does this allow us to sense new things? Well, what you find is that this is your quantum state at the end. And if you look at the probability of being in either the ground or the excited state, you see the probability depends on the phase between this arm and this arm. Okay, so it's in the same way that Mach-Zehnder interferometry, you're measuring the phase difference between light that's gone along your two arms. Here, you're measuring the phase difference of the light that's gone between the two arms of this interferometer. Now, this is fully symmetric, this system. So if like there was vanilla physics, we would expect the phase difference to be 0. Okay, so you'd expect that if you started in the ground state, you'd end in the ground state. If you're accelerating under gravity, which of course you are, that phase difference is not going to be 0. But more interestingly, if you've got some oscillating dark matter field, which is oscillating your energy levels, that's also going to give rise to a phase difference. And by measuring these two probabilities, measuring the number of atoms in here and here and here, what you can do is you can then extract what that phase difference is, and that again gives you sensitivity to your oscillating dark matter couplings. So if you're causing the atomic fine structure constant to oscillate or something like that. So that is kind of the principles of atom interferometry. And people, I mean, I've just given you a very kind of basic thing. When people actually build these, you may have heard of these big, there's like a big, they call it the terrestrial, very long baseline at TVBLA atom interferometry, can't spell, but TVBLAI. There's a number of global, there's a number of different collaborations, big, large-scale collaborations, including AION, which is a UK-based atom interferometer. And we've got MAGIS, of course, which is based at Fermilab, the Very Long Baseline Atom Interferometer, which is in Hanover. And all of these things, the idea is to upscale typical atom interferometers, which are normally on like the kind of tabletop scale, to scale them up to very long baselines. And by very long, I mean anything from kind of 10 meters. There's already an operational 10-meter atom interferometer in Stanford, which is Jason Hogan, Mark Kasvich. MAGIS is going to be 100-meter. There's hopes of having a kilometer. And by kilometer, I mean, you've got, what they actually do is they have two different interferometers separated by this long distance. And why that's good is it means that you're able to, if you've got this big distance and you're operating them with the same lasers, you can get rid of all kind of laser phase noise. So that's a very, very exciting prospect. And the second thing, when I showed you my simple interferometer diagram, the second thing I didn't tell you, I only showed one laser. In practice, what they actually do is they have two lasers that fire counter-propagating pulses from opposite ends of the beamline, baseline even. And the idea is that instead of realizing your beam splitter with one pulse, you realize it with like n pulses, and the same with the mirror. And what that does is the more pulses you have, the more momentum that's being transferred between the two arms of your interferometer. And as a result, the larger the space-time area of these things, and in turn, the greater sensitivity to the phase. So the two differences between the simplified version I showed you were, one, you've got two of them that allows like noise cancellation. The second thing is you've got more pulses, so you've got a wider space-time area and a greater sensitivity, and that's called large momentum transfer techniques. So that's kind of the idea there. So again, what is the status of these things? Well, 10-meter towers exist. There is one in Stanford, which is operational. There's one in VLBAI in Hanover, which again started taking data, I think, in August. The MAGIS 100 is in operation. AION, they've got a 10-meter one in operation, or they're building in Oxford. There's talk about doing a 100-meter or a kilometer one at CERN. ACE, I think they call it atom interferometer at CERN experiment or something like that. So there's kind of various different things in the pipeline. But in order to get sensitivity to new fundamental physics, in order to get sensitivity to ultralight dark matter, or eventually perhaps gravitational waves, you need very, very long baselines. So you need order kind of 100-meter kilometer baselines. And the reason for that is that you need your atoms to be in free fall for a very long time. So you need this T time to be very, very long. The second thing you need is that you need to do lots and lots of these momentum pulses. So in practice, you don't realize the beam splitter with just one pulse. In practice, you have maybe 1,000 pulses, perhaps even more in the future, depending on technological limitations. Now, in order to support these very long baselines and very high atom optics, you need your transition to be very, very narrow. So this means that if you want to build an atom interferometer, you need to do it on a clock state. And this is what's given, or if you want to build a long baseline atom interferometer, you want to build it on a clock state. People have done it on metastable or states which aren't necessarily clock states, but it's a slightly different interferometry procedure. So for this type of interferometry, we call it clock interferometry. You're literally using a clock. So these interferometers are typically based on strontium, which is an atomic clock. Okay, so as we said before, atomic clocks give a sensitivity to electron masses and photons, dark matter coupling to electron masses and photons. So this really means, because you have to have the same clock, well, typically you have the same clock in the bottom and the top, you can't search for new physics coupling to the nuclear sector. So anything coupling to quarks or gluons we can't get, because remember, before we needed a hyperfine compared to an optical. Here, because it's only optical, you're only doing electromagnetic dark matter coupling to photons or electrons. So we had the crazy idea, don't laugh, is could we combine, or actually, first of all, maybe what I'll do is I'll show you what the state of the field is. So this is, I'm looking at these ultralight dark matter models. This is new physics coupling to photons. So these lines up here are clock comparisons. These dashed lines are what you could do with a terrestrial interferometer. So you see what happens is that the sensitivity is pushed to higher frequencies. And it really opens up a whole new area of parameter space. This is what you could do. This dashed line here is what you could do if you could build one in space, which would get rid of all the backgrounds and obviously give you a much longer baseline. And just to kind of highlight the nuclear clock. So this is atomic clocks. If you have a nuclear clock, you can really see it is a 4 order of magnitude shift in sensitivity. So again, that's not something that's been realized, but hopefully in the future, someone will stand here and give a talk and say that they've actually done this. So that's coupling to photons. Couplings to gluons is far more stark, because remember, for gluons, or for, I think this is actually quark masses, so protons or neutrons, here we can't have atom interferometers. So we've just got clock searches and then again the nuclear clock. So we've seen that interferometry can kind of give us new regions of parameter space. The question now is could thorium be compatible with interferometry? Now, I appreciate this is a very kind of far future thing. We haven't even got a operational nuclear clock yet, and I'm already talking about doing interferometry with it. But I think given the rate of progress and given the potential benefit of thorium to the field, now is really the time to start thinking about its potential applications. And again, atom interferometry is just one potential application of thorium. I hope there are many, many other applications of thorium, and maybe some of you might have other ideas, which would be really, really cool. But I'm going to tell you about this one for now. So, as I said, if you want to do long baseline atom interferometry, you need a clock transition. Now, thorium, it turns out that thorium in atoms, the excited state has a very, very short lifetime. It's only 10 microseconds, okay, which is not suitable for a clock. So when people talk about building a thorium clock, they're actually using an ion, right? So they've removed the pesky electrons, they've now got an ion, and that removes the dominant decay channel. It becomes stable in a lifetime of I think 10 to the 4 seconds, okay? But in atomic form, and in these atom interferometers, because you have clouds of 10 to the 6, 10 to the 8 atoms, you really do need them to be neutral. Unfortunately, they decay. So that puts a fundamental limit on the baselines that you can do and the number of atom pulses that you can do. So whereas typical atom interferometers are looking at, all the 100-meter-kilometer baselines, here we find that the product of the number of laser pulses and the baseline is limited to about a kilometer. And your pipe pulse efficiencies become very low, again, because of this decay. So actually, you can only really do 2 pulses before everything's just decayed. So that's like a really big minus of thorium. But because it is neutral, you can obviously have loads and loads of these atoms, and then your shot noise is just going to go as 1 over the square root of the number of atoms. So that's a big advantage. So then we thought, well, okay, so atoms aren't looking that great. Could we do ions? Well, ions, they're very stable. We can suddenly, we can have very big N, we can have very big baselines, you can potentially do them in space. But ions are charged. So not only is magnetic field noise become an issue, but also you can't have a cloud of ions. So your shot noise statistics become a little bit annoying. So all in all, you're probably thinking, well, come on, hi, this is not looking very promising. But remember, the fundamental sensitivity of thorium was 4 to 5 orders of magnitude better. So the question is, do these disadvantages, can they trade off with this enhancement of sensitivity and lead to new parameter space? And the answer is yes, in an optimistic scenario. So here is the coupling to photons. So again, you can see compared to typical clock experience, it really is pushing you to higher frequencies. You are slightly beating atom interferometers of similar baselines, but you are extending again out into higher frequencies. So that's with an atom. And the same with the ion. So with the ion, you can get several orders of magnitude, maybe 3 orders of magnitude better than the typical atom interferometer at low frequencies, but then it curtails at high frequencies. And that's with a terrestrial one and a space-based one. But the real kind of power, I think, comes in when you want to start looking at new physics coupling to the nuclear sector. So anything which couples to quarks or gluons, potentially affecting QCD. In this case, there aren't atom interferometers, so there's no competing experiment. So in this case, there is the potential to really kind of open up new regions of parameter space. Now, I've talked so far about coupling to scalars. So I've talked about one model of ultralight dark matter which couples in this way. It turns out that spin zero scalar dark matter is not the only model of new physics which gives rise to changes in fundamental constants. In fact, everyone's favorite, the axion. Now, although this is intrinsically a pseudoscalar, and intrinsically you wouldn't expect that to couple to masses, it does actually at one loop. So if you imagine you've got like an odd coupling, if you do that at one loop, you get like an even coupling. It's a very heuristic way of putting it. But it turns out you can actually use these experiments to search for axions as well, which I think is quite cool. So I'll just show you what it is for the QCD axion. So again, the QCD axion is actually causing, because the QCD axion causes the pion mass to change, to oscillate. It causes the thorium transition to oscillate. And again, we can do the same kind of plots. So you can see it does beat typical, these are my clock experiments, nuclear EDM experiments. So it is probing a different region of parameter space. However, you'll see that the parameter space I'm accessing here has already been probed by like astrophysical things, so pulsars, gravitational waves, white dwarfs. Nonetheless, those searches are subject to astrophysical modeling uncertainties. So I think it's always useful to have a test in the lab under a controlled environment. But axions, because it's quadratic, it is suppressed, obviously. So that's perhaps a less of an interesting thing. So I guess the point, what I want to get through with this is that there are many models of ultralight dark matter that people are excited about. People have written models, that solve the hierarchy problem, that come from string theory. The signature of these things is they cause fundamental constants to oscillate in time. And one way of being able to look at that is using atomic systems, so using clocks and interferometers. And that's kind of all I was going to say on that. Does anyone have any questions on clocks, interferometers, or anything that I've blabbed about so far?
Maybe I'll ask it now. So, I mean, you have the other way to make the transition stable is to put it in a solid with a large band gap.
Yeah.
Maybe solid xenon, as some of us like.
Yeah.
So could you do an matter wave interferometer in a solid?
Exactly. This is I think the direction which, and I don't have the knowledge to do this. But if you could have some system where it had been, so they're talking about building clocks. When they build clocks, they'll either do a solid state clock or they'll do an ion clock. Now, the type of interferometer I've talked about is free-fall interferometry. But ideally, if you could either have it, I'm not sure how it would work in a lattice, but if you could have this in a molecule, then you could do free-fall if it was in a molecule.
Maybe I'll be very specific. What about a microparticle of solid noble with thorium in it? I
think if you could do that, I think that would be really cool. If there was some way of making it, if there was some way of stabilizing, so the difficulty is you need to stabilize, you need it not to be decaying. You also need to make sure that the energy of your laser is above the ionization energy. So if you could somehow get that to work and you can have a neutral system, this could be really powerful, because the things I've shown you, if it was if everything was working as it was with strontium, you'd literally expect a 4 order of magnitude. I mean, you'd be literally hitting, you'd be literally wrong plot maybe. If things are working as expected, you could literally get 4 orders of magnitude, 5 orders of magnitude down here, which would be extraordinary. But it clearly doesn't work with neutral atoms or ions. So if there was some way of doing it, I think that would be really cool. And I reckon there's probably other things that could be done with thorium doped in, even if it wasn't a clock transition, there might be something interesting that could be done. But yeah, just food for thought. Any other questions?
On the sensitivity plot for the scalar couplings, the y-axes are d m dot and another one was de.
Yes.
Are those couplings to clock measurement parameters or
Good. Yeah, this is, so if I go back to my very good question. So these are couplings to different standard model terms. So the DE is the coupling to photons.
Yep.
So it's just saying your fundamental field is coupling to photons. It's causing the fine structure constant to oscillate in time. And the DM hat was the coupling to quarks.
Okay, yeah, all right, thank you.
So, yeah. So, yeah, I think thorium is potentially something which is going to be really cool to detect new physics coupling to QCD. As I said, everyone's really focused on, this clock transition, but there must be more things that can be done with it and different ways maybe this system could be explored. And I think, it's really the time now to kind of jump on this bandwagon because it's getting a lot of, there's been like all these ERC grants and it's getting a lot of noise. And the rate of, being able to isolate thorium and have it in, trap it in systems is it's quite extraordinary, the rate of development. Any other questions? Yeah.
Do you have a sense of the frequency of these dark matter oscillations?
Yeah. So it depends. It can literally be anything from like 10 to the -6 up to 10 to the 6. Typically, if it's actually dark matter, we're more interested kind of in this range, which is partly why we're interested in interferometers, because a lot of this, like below about 10 to the -19, you may have heard of these like fuzzy dark matter models. Some people say that this is all ruled out if it's like 100% of the dark matter. So this is why clocks perhaps are less interesting. But if you've got something which is up here, then that could easily be 100% of the dark matter. So yeah, I mean, atom interferometers, their typical sensitivity is about the hertz or 0.1 hertz. But I'm very much of the viewpoint that we don't know what dark matter is, but we want to be able to probe these things as broadly as possible. And if there are ideas of probing new areas of parameter space which haven't been probed, that's exciting. I should also say, from a theory point of view, people get more excited as you get into this red band because it's more technically natural. It's just it's kind of a theoretical bias, but basically if you have some coupling, you get like loop corrections to the mass, but we're saying, oh, the particle's really light, but then if you've got corrections to the mass, that spoils it. So we get more excited when you're down here. So if you could get things that get into this red band, that's like the kind of people be more excited, I think, from a theoretical point of view.
Could you talk more about the red band? Because that was going to be my question, is like, what does it mean? And like, I read it at first as like, if you can hit this line, a good exclusion has happened, but maybe it's the opposite of that.
If you can hit this, so everything above my lines it would be excluded, or but this is just a guide to the eye. It's saying that if you have, so the problem with light scalars is that you've got the mass of the particle, it's very light, but it's coupling, it's particle physics, but you get like a loop correction basically. So every particle that couples to it kind of changes the effective mass. So the idea is that if you can get into this region, the change to the mass does not prevent you from being light, if that makes sense. So if you want to be out here, in order to keep your thing light, you need finely tuned cancellations, basically. So you need kind of interactions with different particles to cancel off. And people are a bit like, oh, that shouldn't happen in nature. It happens with the Higgs mass. So some people say, well, if it happens with the Higgs, then it's not really such an issue here. But if you're of the school of thought that you worry about these finely tuned cancellations, if you have a model that lives in this space, it's more well motivated. So that's kind of the idea there. So it's not that it's been excluded. This is just kind of to guide your eye to say, well, ideally we want to build experiments that get down to this point.
Is there anything keeping those lines from being zero? Like, can these couplings just continue going down?
Yeah.
There's nothing bounding them from below.
No, okay. No, it's just you have to build a very good detector. Yeah.
It's somewhat a naive question, but maybe it's related to what we were talking about. So in standard model, you can't just add arbitrary field into your model because that could cause bathing. And I was wondering, is the phenomenology here like solid, or we're just being agnostic of we can try this and this might be the dark.
Yeah, very good. So these are models that have been proposed, and they are things which haven't been ruled out by existing experiments. So for example, these light scalars, they give rise to long range forces. Similar to the fifth force is probably you're probing in your ultralight dark matter, your dark matter impulse thing, but a different nature, right? But so these models, the kind of main signature that we would see, perhaps if we weren't looking specifically for the change in frequency, would be that they give rise to a long-range force. So that's been probed by these torsion balance experiments, wash, microscope, and that's above these lines. So everything above, everything below the blue and the purple doesn't spoil like life as we know it. But you're right, yeah. I mean, this is why whenever you propose a new model, you need to think about every kind of way that that model could feed into affecting nature. And yeah, so these models, they're not totally arbitrary, and the axion is well motivated for its own reasons, solves a strong CP problem. So there is motivation behind these models. Does that answer your question?
Yeah. Thank you.
Any other questions? No, in which case, okay, I'm gonna.
Oh,
yeah.
you have more?
I was gonna go on and talk about
That's
the
fine.
optomechanics, but
No, optomechanics is great. Yeah.
yeah, sorry. You guys are all experts though, so I will say I probably don't need to do. I'll just do the introduction to dark matter then. So now we're going away from scalars, we're going to vectors, okay? So we've got a new vector boson. It's like a photon, but it's not a photon. And particularly, we're going to have one that couples directly to the standard model. So this is just like kinetic energy. This is a mass term. And now I've got something which is coupling to this, which is just neutrons, okay? So we call this a B minus L force because the baryon minus lepton number of your system is conserved. And the signature of this, so much in the same way that the ultralight scalars cause fundamental constants to oscillate, this causes oscillatory forces on macroscopic objects. And the size of the force depends on the neutron number, or basically the mass. So the signature that you'd look for is you're looking at a differential acceleration between two materials that have different proton to neutron ratios. So in the case of an optomechanical system, you're looking at a differential force between, for example, either two objects of different materials or an object in the trap of a different material. So you're all experts at optomechanical sensors. I don't need to tell you anything about this, but I just want to kind of just say part of the motivation or the way that we were thinking about this when we were coming up with this experiment, which is that, as you all know, optomechanical sensors are, in the ideal case, limited by two sources of quantum noise, your back action and your shot noise, and they behave inversely with the laser power. So if you want to build the best, if you want to have your like standard quantum limit, that's going to be at the point where your shot noise and your back action are minimized. And it turns out that happens, so the power, you tune the power of your system to the point where these two things are equal. So we then started thinking, well, how does the standard quantum limit, so you tune the power to get to the standard quantum limit, how does that matter in optically levitated systems or optically trapped systems? So in an optically trapped system, obviously you're using the same laser field both for your trapping and your readout. And this means crucially that your mechanical frequency is depending on your laser power. So you can imagine you have your system, you try and, for example, tune the power to get to SQL. So for example, tune the power to reduce the back action and raise the shot noise. But when you do that, you actually change the resonant frequency of your trap. So this has an implication because when people think about searches for ultralight dark matter, because you're looking for a wave, you might naively think, well, I want to be on resonance. You want to do a resonance-based search. But actually, what we show is that's not necessarily the case. So actually, for the systems we were looking at, and for nanoparticle systems, as the same conclusion holds, is that actually your standard quantum limit, the point where your back action and your shot noise are minimized, doesn't actually occur on resonance. It actually occurs when your trap frequency is slightly below the frequency you're looking at. So if you want to get the best sensitivity with these systems, you don't actually want to do a resonance search. You want to do a SQL search. You want to tune the you want to tune the power so that you're on SQL. And then the second thing we started thinking about was, okay, well, how does the SQL noise depend? how does your sensitivity depend on the mass of the sensor? So when you've got a nanoparticle and you're in the Rayleigh scattering regime, it turns out that the SQL noise that you get, that you compute when you do this minimization, scales in the same way as the sensor mass of your dark matter signal. So you can imagine, you might think, oh, well, the dark matter force is scaling with mass. So perhaps I could just levitate a bigger object and that would give me a bigger sensitivity. It turns out the mass scales in the same way, or the SQL noise scales in the same way. And that means that, even if you increase the mass, it's not going to increase your signal to noise ratio. But if you can get into the ray optics regime, so where the size of your levitated object is much greater than the wavelength, in this case, you do actually find that the SQL noise, the best noise that you can get, scales less steeply with the sensor mass than the dark matter signal. And this gives you a lever or an extra tool, because it means that in this case, if you increase the mass, then obviously you are buying something in the sensitivity. So you have an extra lever to kind of improve things. So kind of the point of this analysis, and I'm sorry if I've kind of made a hash of explaining this, but the point is that there's motivation to be able to trap large objects which are actually in the ray limit, because in this case, if you can then increase the mass, your signal to noise ratio is going to improve, and that's going to benefit your search. So this is kind of the motivation behind this work, which was with Peter Barker from UCL, Andy Geraci at Northwestern, and Louis, who's at Mines at the moment. And the idea was, could we develop some kind of new system or some new trap, which is specifically tailored to searching for these oscillatory ultralight dark matter forces? And from this, as you can see, we've kind of argued that we want to be able to levitate large masses. And I know there have been some proposals for levitating large masses, I think perhaps in this group, but it's certainly been something which has been less studied than nanoparticles. So what is the idea? So the idea is a new kind of trap. It's a optically levitated trap. We're sensing, this is our sensing direction, the X direction. We've got two counterpropagating beams which are forming a harmonic oscillator. We have an object which is trapped, as you can see, it's trapped away from the foci. So it's different to when you're trapping a dielectric absorber or emitter. And its weight is supported by a vertical beam. And this trap is designed to be able to trap objects up to kind of like we predict 0.2 milligram sensors, potentially with a very high power laser, potentially you could get higher. So again, we kind of foresee this just to be kind of a silica wafer, I guess, like a slice, and supported by this vertical beam. And we then use this to detect beam. We hope that this could be a way of detecting this B minus L. So in this case, again, you're literally just looking at the motion of this optical, you're looking at the motion of this sensor relative to the optical table. So the idea is that this is made of tungsten. The lab table is made of tungsten. This is made of silica. The reason we choose tungsten is because you want as larger proton to neutron ratio as possible in order to kind of increase the difference in the force of the dark matter on this and the force of the dark matter in that, which is what drives the relative displacement. And that's the sensor. We call it molecule. Yeah. And this is kind of the sensitivity that we are getting. So again, this is with what you could get potentially with a 0.2 milligrams. So it's about half an order of magnitude than the best results from microscope. And then if you could do a 0.8 gram sensor, I think it's probably slightly ambitious, but that could lead to kind of 2 to 3 orders of magnitude improvement. And one thing I really want to highlight with this graph is that you may think, well, LIGO Virgo, I mean, what is that? That's basically like a massive mirror. So that is basically a massive levitated system. But yet, that does comparatively worse than what potentially we could do with a tabletop experiment. And that really drives home to me, well, okay, first of all, why is that? Well, the reason is that LIGO Virgo, of course, is taking a differential measurement between two different mirrors. And as a result, it's not sensitive to the force directly, it's sensitive to the gradient of the force, which is suppressed. So even though LIGO is like a multi-billion pound experiment, and it's very good at what it does, its sensitivity to this B minus L dark matter is not as good as what could potentially be done in the lab. And this to me really drives home the fact that we do need experiments specifically targeting different dark matter theories or dark matter ideas. And I think that was really kind of the idea behind this work here, is that we wanted to kind of come up with something from first principles that was tailored to work for these to sense these kind of signatures. And it is, it's a first go at this. There's probably other ways, other things that could be done. And I think there's always merit if you've got systems in the lab of thinking what other things can those systems can be done for. But there's also merit in, I think, thinking about what is the signal we want to detect and what would be the optimal setup to do that. So it's kind of a two-pronged approach, I guess. But I'm a very dumb theorist, so I'd love to hear your thoughts and your ideas on all of this kind of stuff. So I think I've probably talked. Yeah.
Before we move on that, but why does the orange SQL scan diverge at high frequencies?
Yeah, good. So this was assuming infinite laser power. This one, which I think obviously is slightly yeah. So I think this is like we took like the highest lab grade laser. I think it was like kilowatt laser. Like it's still crazy. I know it's still crazy. But this is I will say that you don't need to operate at these powers. This is just assuming that we're on SQL. So the high laser powers that you need is really to make sure that you're hitting SQL. So you could easily just say, even if you had like 100-watt laser, you could easily do something, but you'd find that it goes like much steeper before because you're not able to hit SQL. So what we find here is that this is the point where it's like 100 kilowatts or something, like something crazy. But you could easily cut it off much before and at far more reasonable laser powers. But yeah, we just wanted to show what was feasible should you have a very high laser power output disposal, which I realize is not something that could be done probably in a typical lab-based experiment. But yeah, very good question. Any other questions?
Yeah, why do you want a levitated rather than a suspended system for this?
Very good. So it's actually all to do with the noise. So we wanted to consider we did an analysis with a string, for example, and it turns out if your string is at 100K, which was what we assumed the temperature of our system was, your noise is well above your shot noise per fraction. So you'd be completely dominated by the sound noise of the system. In order to bring this line down to kind of the level that we need, you'd need to be operating, I think it was like 10 millikelvins or something, which I imagine is quite challenging to achieve. So this experiment could be done with a suspended system, but in that case, you would need to be kind of cryogenically cooled. And Andy Geraci, who was on this paper, was like, no. So we went for optically levitated. I think it's a unique trap design. It's a different kind of trap. There's probably other things that could be done with this sort of trap. But yeah, that was the reason. It's all to do with the thermal noise. I think particularly because the lasers are going to be heating up the sensor, and I think we calculated the equilibrium temperature of the sensor was about 100 Kelvin. So if you've got a string attached to that sensor, even if you cryogenically cooled the string, you're going to get some transfer from the sensor itself. Very good question. So I'll just briefly give you my conclusions, and then so basically I'm excited by quantum sensors. I'm excited by everything you guys are doing in the lab. It really is a kind of prime opportunity to probe new fundamental physics at the feebly interactive frontier. It's very easy to think, people have done like all these experiments with dark matter for ages, they haven't found anything, but they have really limited, I had that plot at the beginning. Most work has been done really in this center, and there's a whole landscape of bizarre and bewildering effects out there to explore, many of which are specifically naturally seem to work really well for the sort of systems that you guys are developing in the labs. I think it's a really exciting opportunity. Of course, we have atomic clocks and interferometers, which are kind of paving the way in certain types of dark matter. Thorium, I think, is going to be a real game changer. So if you can think of new ways of using thorium, I think it's going to be really exciting. And I think, you know, again, I've just given you one optomechanical new idea. But I think that there must be so much stuff that's going out there. And I really don't have the expertise to know what the best direction is, but I think you guys probably do. So I think there's probably some really cool, not new kind of phenomenology that could be done with these systems as well. And I'm just, thank you so much for letting me be here today. It's been so inspiring to see what you're all doing. And I'm really excited to see what you guys do in the future. So thank you again for listening.
Santa, we've had lots of questions, but I don't know if there's one or two more. Maybe I'll ask one. So, I mean, you, yeah, like you say, you maybe need 100 kilowatts to levitate that much mass, but like, how does it, if you were to break it up into little chunks, so you don't need all that 100 kilowatts on one particle, how does your SQL thing scale?
So do it like an array.
Yeah, like an array of.
Yeah, good point. So that's a very good point. So yeah, so to get to SQL, you wouldn't need, so the issue with the power, with the trapping power is just to get it on SQL. But if the mass was less, then, so I think you'd lose because, no, so overall you get a factor of n, right, from the number of things. So that would buy you back some. I think maybe it would be less. I need to work this through carefully. I think, yeah, you'd need to, actually maybe you wouldn't lose at all. I need to work this through, but that's a good question. But I think, again, this could be done similarly with an array, I think, as long as you had the same total mass. Yeah.
That's what I was unsure. There's a root n in there, and whether it's the same root n you have in the SQL or not, I'm not sure. But yeah, we could.
Yeah. Yeah.
And but you might need to coherently read out the array or something.
Exactly. Yeah. I think you might need a coherent readout. Yeah.
Okay. Great. Cool. Any other questions? Okay. If not, thank you.
Thank you very much.